Imagine floating in the profound silence of deep space, a realm where the sun is a distant, brilliant star, its warmth a fading memory. Out here, 3 times farther from our star than the Earth, the cold is absolute. It's a place of stillness where the universe sleeps. Comets, those ancient wanderers of ice and rock, are meant to be dormant here, their fiery tails and glowing comas reserved for their dramatic, sun-scorched passages through the inner solar system. Everything is supposed to be frozen, quiet, practically dead. And then you see it, an object that refuses to obey the rules, a traveler from an unknown star system, an emissary from a place with different physics, different chemistry, a different history. This is 3I Atlas, and it is doing something that should be impossible. It is hemorrhaging water into the void, exhaling a staggering 40 kilograms of vapor every single second. It's not a trickle, it's a torrent. In the freezing abyss, this comet seems to breathe. Astronomers, watching through their most powerful telescopes, can only whisper, "It's acting alive." But the story of this impossible object is only just beginning. Its breath is laced with mysteries, a strange green glow of nickel without its constant companion, iron, a delayed release of cyanide from its heart, and a chemical signature that whispers of an origin billions of years older than our own sun. It is a time capsule from an epoch of the galaxy we can only dream of seeing. As this interstellar enigma hurtles through our cosmic neighborhood, other strange events unfold. On Earth, citizen scientists, amateur astronomers with a passion for the unknown, stumble upon colossal, ghostly rings in the radio sky, the largest odd radio circles ever seen. In our own solar system, the planets Mercury and Ceres dance into a rare, perfect alignment in the October skies, prompting whispers and speculation on social media. Are these events connected? Is there a pattern in the chaos? And as if to add another layer of unreality, a commercial spaceflight by Blue Origin in the same month is shrouded in such an unusual silence that people begin to ask, did it even happen? Stay with me. We are about to confront these unsettling questions, weaving together these disparate threads into a single, multi-story tapestry of cosmic mystery. We will explore the science, the speculation, and the profound human need to find meaning in the things that defy our understanding. If these mysteries have you hooked the way they have me, make sure to hit that like button and subscribe to Stellify Science so you don't miss a single update as this story unfolds in real time. Drop a comment below with where you're tuning in from, what time it is there, and your theory on these world-changing discoveries. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this. So, thank you for having our back. The laws of physics are not suggestions. In the vacuum of space, they are absolute. One of the most fundamental is how energy dissipates over distance. The light and heat from our sun spread out in a sphere, and its intensity drops off with the square of the distance. Double your distance, and you only receive 1/4 of the energy. This is the inverse square law, and it governs the lives of comets. For a comet, solar energy is lifeblood. It's the engine that drives its activity. When a comet gets close enough to the sun, the ice on its surface doesn't melt. The pressure is too low. Instead, it sublimates. It turns directly from a solid into a gas, erupting from the nucleus and carrying dust with it. This process creates the iconic coma, the glowing head, and tail. Water ice, the most common volatile in our solar system's comets, needs a certain amount of energy to begin this process in earnest. Typically, this turn-on point is somewhere inside the orbit of Jupiter, around 2 to 3 astronomical units, AU, from the Sun, where 1 AU is the distance from the Earth to the Sun. 3I's Atlas shattered that rule. The first clue came from SWIFT, a NASA space telescope not designed to study comets, but to hunt for the most violent explosions in the universe. Gamma-ray bursts. SWIFT has a powerful ultraviolet optical telescope, UVOT. In early 2025, when it turned its ultraviolet eyes toward 3I Atlas, it spotted something that, according to our models, should not have been there. It saw a vast, shimmering halo of hydroxyl molecules, OH. Hydroxyl is the ghost of water. When a high-energy ultraviolet photon from the sun strikes a water molecule, H2O, it has enough energy to snap the chemical bond, breaking it into a hydrogen atom, H, and a hydroxyl radical, OH. Hydroxyl is unstable and glows faintly in the ultraviolet. Seeing it is an unambiguous sign that water was just there and it was being destroyed by sunlight. And SWIFT saw a lot of it. The numbers were staggering. At a distance of 3.51 AU from the Sun, well outside the typical activation zone, 3I Atlas was releasing 1.35 ACE 10^27 water molecules every single second. That translates to 40 kilograms per second, every second. To put that in perspective, that's like dumping a small car's worth of water into space every minute. This wasn't a whisper of activity, it was a scream. Our solar system comets don't do this. Not out here. At this distance, they are cold, dormant, practically dead. The solar energy is simply too weak to drive such prolific sublimation of water ice. This immediately set 3I Atlas apart from the two previous interstellar visitors. The first, Oumuamua, was a complete enigma. Dry as a bone, with no detectable outgassing. Just a bizarre, tumbling rock speeding through our neighborhood. The second, 2I Borisov, was active. But it behaved exactly like our comets do. It followed the script. It was predictable, which in a scientific sense was reassuringly boring. 3I Atlas is neither of those things. It's alive in a way that shouldn't be possible. The question hanging over every astronomer is simple. How? What mechanism could possibly drive this? Several hypotheses are on the table, each more exotic than the last. Exotic ices. Is it possible that the comet's primary volatile isn't water? Maybe it's a different kind of ice we don't often see, something that sublimates at far lower temperatures. Carbon monoxide, CO, and carbon dioxide, CO2, are common in comets, but they usually act as secondary drivers. Could 3I Atlas be made of a material where these supervolatiles are so abundant they can physically eject water ice grains into space, even in weak sunlight? Amorphous ice. When water freezes slowly, it forms a neat, crystalline structure. But if it freezes incredibly quickly, in the vacuum of space, it can form amorphous ice, a disordered, glassy state. Amorphous ice is unstable. When gently heated, it can suddenly snap into a crystalline structure, releasing a burst of energy. This energy could be enough to sublimate itself and surrounding ices, triggering a chain reaction. Perhaps 3I Atlas is made of this high-energy ice, a relic of its formation in a particularly cold, strange environment. Internal heat. Could the comet be warm on the inside? It sounds impossible for a small body that has spent billions of years in the interstellar deep freeze. However, some models suggest that if a comet contains enough radioactive elements like aluminum-26, their decay could have melted its interior long ago, creating a liquid water core insulated by a thick outer crust. Could residual heat from this ancient process still be leaking out, warming the ice from below? The water is just the beginning. 3I Atlas is also leaking other things: cyanide, nickel, carbon dioxide, in concentrations that make no sense. Each new observation adds another layer to the mystery. This isn't just a comet behaving oddly. This is a comet that seems to be operating under a completely different set of physical rules. Rules written in another star system. And now it's here, giving us a front row seat to processes we've never seen before. In the grand cosmic forge of stars, elements are not created equal, but they often form partnerships. Iron and nickel are one such pair. They are born together in the hearts of massive stars and flung into the universe during supernova explosions. They have similar condensation temperatures, meaning they solidify out of a hot gas cloud at around the same point. As a result, in the asteroids and comets of our solar system, where you find one, you almost always find the other, locked together in minerals and in predictable ratios. It's one of those cosmic constants we've come to rely on. Except 3I Atlas didn't read the textbook. The European Southern Observatory's Very Large Telescope, VLT in Chile, is one of the most powerful optical instruments on Earth. When its spectrograph was aimed at 3I Atlas, it sliced the comet's faint light into a rainbow of constituent colors, a spectrum. Spread across that spectrum were dark absorption lines and bright emission lines, the unique barcodes of the elements present in the comet's coma. What astronomers saw made them do a double take. The emission lines for nickel were blazing bright, strong, unmistakable, but the lines for iron were either completely absent or so vanishingly weak they barely registered. Nickel without iron. It's like finding smoke without fire, footprints without feet. At a distance of around 2.8 AU, astronomers calculated that nickel was pouring off the comet at a rate of about 5 grams per second. That doesn't sound like much, but it's a continuous, steady stream, with its partner iron nowhere to be seen. This isn't a glitch. It's the comet telling us something fundamental and bizarre about its composition. The explanations are all extraordinary. Chemical fractionation. Perhaps in the unique environment where 3I Atlas formed, nickel and iron were chemically separated. Imagine a scenario where nickel preferentially bonded with highly volatile molecules, like carbon monoxide, hitching a ride with the ices that sublimate easily. Meanwhile, iron got locked into more refractory, rocky minerals that need much higher temperatures to vaporize. This would create the decoupling we're seeing, where the easy-to-burn fuel, nickel compounds, is released first, while the hard-to-burn fuel, iron minerals, stays behind. Organometallic compounds. This is a more specific version of the first idea. On Earth, we can create molecules like nickel carbonyl, NiCO, where a nickel atom is bound to 4 carbon monoxide molecules. These compounds are extremely volatile. If 3I Atlas formed in a protoplanetary disk exceptionally rich in carbon monoxide, perhaps nickel got trapped in these kinds of molecules. When a little sunlight hits them, they decompose, releasing atomic nickel gas into the coma, while iron remains locked in solid grains. Space weathering. An object wandering interstellar space for billions of years is not untouched. It's constantly bombarded by high-energy cosmic rays and ultraviolet radiation. This sustained assault can profoundly alter surface chemistry. It's possible that this radiation processing created a very thin, nickel-rich surface layer, while iron was buried or chemically altered into a non-volatile form. What we're seeing might just be the comet's radiation-damaged skin, not its true bulk composition. A truly alien origin. This is the most exciting possibility. Stars are not all identical chemically. Older stars, stars from different parts of the galaxy, stars born from gas clouds, enriched by different types of supernova. they all have slightly different recipes. Perhaps 3I Atlas comes from a place where nickel was genuinely far more abundant relative to iron than it is in our neighborhood. Its birth star was chemically odd, and that oddness is now written into every molecule of this comet. Of course, spectroscopy is hard. It's possible iron is there, just below the VLT's detection limit, its faint signal lost in the background noise. But as the comet gets closer and heats up, if iron still doesn't appear, that would be revolutionary. It would tell us that planetary systems can form with such different metal chemistry that our models need a complete overhaul. Every new spectrum of 3I Atlas is a test, a chance to either confirm our understanding of the universe or shatter it. And right now, it's doing more shattering than confirming. The brightening of a comet should be a graceful, predictable affair. As it falls toward the sun, the increasing solar energy should cause a smooth, steady increase in sublimation, releasing more gas and dust, making the comet brighter. The physics is straightforward. 3I Atlas, however, is anything but straightforward. Observers noticed something strange about its color. Early on, far from the sun, the comet looked relatively neutral, perhaps slightly reddish, which is typical for distant, icy bodies whose surfaces have been tanned by cosmic rays. But as it moved closer, it began to turn green. Not a subtle shift, but a vivid, eerie green that became unmistakable in photographs. This green light is the spectral fingerprint of two specific molecules, diatomic carbon, C2, and cyanide, CN, along with the atomic nickel we've already discussed. All three emit strongly in the green part of the spectrum. The fact that their brightness wasn't just increasing, but accelerating, was the key clue. The increase was superlinear. Here's what that means. The inverse square law dictates that if you have the distance to the sun, you get 4 times the sunlight per square meter. The comet's activity should increase by a similar factor, but 3I Atlas's green emissions were climbing even faster than that. Something new was being unlocked. Some new process was kicking in. Astronomers call this switch-on behavior. Imagine a series of temperature thresholds. Threshold 1, far out. A supervolatile ice, like frozen carbon monoxide, starts sublimating. This is the first switch. Threshold 2, closer in. The comet crosses a new temperature line, and suddenly another less volatile ice, perhaps the strange amorphous water ice, begins to sublimate. The gas production jumps. New emission lines appear. A second switch is flipped. Threshold 3, closer still. Another temperature is reached, triggering the breakdown of complex organic molecules on the surface, releasing the cyanide and diatomic carbon. The third switch, 3I Atlas, seems to have multiple switches, and they're flipping at distances that don't match our experience. The water turned on first, way out at 3.5 AU. Then came the cyanide and nickel, blazing green as the comet warmed further. Each emission suggests a different volatile reservoir being tapped. Several physical models could explain this. Extended icy grains. Instead of all the activity happening at the nucleus surface, imagine small, icy grains being lifted off by the initial, weak outgassing. These grains float away, forming a cloud around the comet. As they drift, each individual grain is exposed to sunlight from all sides. Each grain reaches its own personal sublimation threshold, creating a distributed source of gas that grows exponentially. Thermal fracturing. Comets are dirty snowballs, a fragile mix of ice and rock. As the surface heats and expands while the interior stays frigid and contracted, immense stresses build up. Eventually, something cracks. These cracks can propagate deep inside, exposing vast new surface areas of fresh, volatile ice that were previously insulated. The comet experiences a dramatic outburst. 3I's Atlas might be cracking itself open as it heats, revealing layer after layer of its frozen chemistry. This isn't entirely alien. We've seen comets in our solar system have sudden outbursts or split apart. But 3I Atlas is doing this on a schedule and at a distance that feels almost deliberate. The tension is building among astronomers. As it continues its inward journey, will more switches flip? Will we see new molecules we didn't expect? This isn't a predictable object. This is a cosmic drama unfolding in real time. Every object in space carries its history written in its trajectory. An orbit is a story of gravitational encounters, a map of where an object has been and where it is going. The orbit of 3I Atlas tells a story that spans billions of years and thousands of light years. The technical term for its path is hyperbolic, with an eccentricity greater than 1. In simple terms, this means its path is an open curve, not a closed loop like a planet's orbit. It came from the vastness of interstellar space, will make a single, sharp turn around our sun, and then depart, never to return. It is unbound, a free agent, a true wanderer. To pinpoint its origin, astronomers performed pre-covery. They searched through archives of old sky surveys for images of the comet taken before anyone knew it was interesting. They found it, a faint smudge on images going back to when it was 6.4 AU away, still inbound and cold. By stitching together these old and new observations, they reconstructed its trajectory with incredible precision. That trajectory points outward, back into the galaxy, but not just anywhere. By combining the comet's path with data from the Gaia Space Telescope, which has mapped the positions and motions of nearly 2 billion stars, astronomers can trace its motion backward through the galaxy. The answer is surprising. Our Milky Way galaxy has structure. Most stars, including our Sun, live in the thin disk, a relatively flat plane of younger, metal-rich stars. But there's also a thick disk, a puffier, more spread-out population of older stars that orbit on more tilted, eccentric paths. These stars are chemically different. They formed earlier in the galaxy's history, 7 to 10 billion years ago, when the universe had fewer heavy elements. The trajectory of 3I Atlas strongly suggests it came from the thick disk. If this is true, then this comet could be substantially older than our entire solar system. Our sun and planets formed 4.6 billion years ago. 3I Atlas could be a relic from a star system that was born, lived, and possibly died before the sun even ignited. Think about what that means chemically. The gas cloud that collapsed to form our sun was enriched by billions of years of supernova explosions. The gas cloud that formed a thick disk, star 7 billion years ago, had less of that enrichment. Its star system would have had lower metallicity, fewer heavy elements like iron, magnesium, and silicon. This might be the master key to its mysteries. A lower abundance of rocky elements could explain the weird metal ratios. Different initial conditions could lead to a dominance of CO2 over water. This comet might be a chemical fossil from a time when the galaxy was younger and the periodic table was emptier. Of course, tracing an object's path back through billions of years of galactic motion is fraught with uncertainty. Gravitational nudges from passing stars and giant molecular clouds can muddle the trail. But the fact that a thick disk origin is even plausible is extraordinary. We might be looking at a survivor, a time capsule from the ancient galaxy, delivering a sample of primordial chemistry to our doorstep. A comet is far more than just ice and rock. It is a cargo ship, carrying an exquisitely preserved inventory of the molecules from its birth environment. And 3I Atlas is carrying some very strange cargo. We've talked about the water, but the carbon dioxide is the real shock. In our solar system's comets, water is the king. It's the main volatile, the primary driver of activity. CO2 is a supporting player. In 3I Atlas, the script is flipped. Some measurements suggest that a staggering 95% of the volatile emissions are carbon dioxide, with water as the minority component. That is completely backward. Why would a comet be so CO2 rich? One possibility is formation temperature. The snow line in a protoplanetary disk is the distance from the central star, where it's cold enough for a particular volatile to condense into ice. Carbon dioxide ice condenses at a higher temperature. It's easier to freeze than water ice. If 3I Atlas formed in a warmer region of its disk, closer to its parent star than our comets did to the Sun, it might have preferentially incorporated CO2, while much of the water remained as gas. Then there's the cyanide, CN. It's a common cometary molecule, but in 3I Atlas, it appeared later in the warming sequence than the water. This delayed appearance suggests it might be trapped in more complex organic molecules that need extra energy to break down before releasing their cyanide component. All these ingredients, water, complex organics, cyanide, are the key precursors in prebiotic chemistry. If you wanted to design a package to seed a barren planet with the building blocks of life, you'd include exactly these things. This inevitably brings us to the elephant in the room, the panspermia hypothesis. This is the idea that life, or at least its chemical foundations, can spread through space on comets and asteroids. Let's be very clear. This is speculation. There is no evidence that 3I Atlas carries life, but it's not impossible in principle. The challenges are immense. Interstellar space is brutal. For millions of years, the object would be sterilized by cosmic radiation and ultraviolet light, which tear apart complex molecules like DNA. For life to survive, it would need to be buried meters deep inside the comet, shielded by ice and rock. But what might survive are not living things, but chemical fossils. Complex molecules synthesized in the comet's parent system, perhaps in the atmosphere of a planet or on its surface, could be incorporated into the comet and protected. If we could analyze them, they might reveal the atmospheric chemistry of an alien world, or the metabolic pathways from an extinct biosphere. They would be messages written in carbon and nitrogen, waiting to be decoded. This is why some scientists dream of intercepting an interstellar visitor, sending a spacecraft to match its velocity, land on it, drill into it, and analyze a sample. The technological challenges are immense. These objects are moving at tens of kilometers per second, but the scientific payoff would be incalculable. A sample from another star system, chemistry from another corner of the galaxy, answers to questions we've barely learned how to ask. 3I Atlas is too far, too fast. We won't catch this one, but it's showing us what's out there, and it's making us hungry for the next one. Sometimes the most important discoveries happen not because of a sophisticated algorithm, but because of a pair of human eyes and the intuition that says, "That's weird." Let me tell you about odd radio circles, or ORCs. Discovered only in 2019, they are vast, ghostly rings visible only in radio wavelengths. They are genuinely mysterious, and finding them is hard because they're faint and diffuse. Automated algorithms, trained to find bright, compact objects, tend to miss them. Enter Radio Galaxy Zoo, a citizen science project where volunteers visually inspect radio maps. In March 2025, a volunteer flagged something extraordinary. a pair of intersecting radio rings, the most distant and powerful ORC discovered so far. It was found not by a professional astronomer, but by someone volunteering their time to look for the unusual. This highlights a growing reality in science. We are entering an era of data deluge. The upcoming Vera C. Rubin Observatory will generate 15 terabytes of data every night. No human team can look at all of that. We need machines for bulk processing, but we need human eyes to catch the weird edge cases that don't fit any existing template. This brings us to a natural tension in the scientific community. On one hand, citizen science is a powerful tool. It engages the public and can process vast data sets. On the other hand, there is the problem of quality control. Professional astronomers worry about being inundated with false positives. Well-meaning amateurs flagging things that turn out to be instrumental noise, satellite trails, or cosmic ray hits. Every false positive requires follow-up time that could have been spent on genuine discoveries. There's also confirmation bias. Amateurs, like professionals, can see patterns where none exist. This is how you get claims of alien megastructures around Tabby's star, or messages in pulsar signals. Professionals have the backstop of rigorous peer review. Amateurs might not. But these problems are solvable. With training protocols, mentorship programs, and tiered validation systems, where multiple volunteers must flag the same object, the signal-to-noise ratio can be dramatically improved. Could a citizen scientist have flagged the anomalies of 3I Atlas early? The spectral data is public. However, interpreting it requires specialized knowledge. But what about its light curve? Its brightness over time? Many of these are contributed by amateur astronomers. If they had been trained to recognize unusual activity patterns, they might have flagged 3I Atlas's superlinear brightening long before the professionals confirmed it. The future of discovery isn't about replacing professionals with amateurs. It's about partnership. We need professionals for the deep expertise and rigorous validation, and we need citizen scientists for the sheer number of eyes and fresh perspectives. In the era of big data, it's a necessary alliance. In October 2025, the night sky offered a treat. Mercury, the innermost planet, was in a favorable evening apparition, while Ceres, the largest object in the asteroid belt, reached opposition, making it bright and close. On social media, people started connecting dots that weren't there. Mercury is visible, Ceres is visible, and this weird interstellar comet is acting up. Could they be related? Let's be clear. No, there is no plausible physical connection. Mercury's orbit has nothing to do with a comet's outgassing billions of kilometers away. The gravitational influence is essentially zero. These are independent events, coincidentally visible at the same time. But people love patterns. Our brains are hypersensitive pattern detection machines, a trait that helped our ancestors survive. Sometimes, this trait goes into overdrive, a phenomenon called apophenia, or patternicity. It happens with celestial events all the time. Ancient cultures saw omens and alignments. A perfect historical analogy is Halley's Comet in 1910. Astronomers detected cyanogen, a toxic gas, in the comet's tail. Newspapers ran sensational headlines. Panic ensued. People bought comet pills and gas masks. Of course, nothing happened. The comet's tail is an almost perfect vacuum by Earth standards. The amount of cyanogen that reached our atmosphere was undetectable. But the coincidence of the comet's appearance with other unrelated events fueled the panic. We're seeing the same thing now with 3I Atlas. The human brain craves stories and connections because they impose order on a random, chaotic universe. Social media algorithms amplify this exponentially. creating echo chambers where a fringe theory can quickly look like a mainstream consensus. The lesson isn't that people are gullible. The lesson is that coincidences are psychologically powerful, and our brains aren't well calibrated to dismiss them. This matters because it affects how we interpret real anomalies. If you're primed to see conspiracies, the comet's weird behavior becomes evidence of something larger, more mysterious, and perhaps even artificial. On October 8th, 2025, Blue Origin's mission NS-36 launched, flew, and landed. Another routine space tourism flight. That was the official story. But what was strange was the silence. No viral videos, no trending hashtags. A commercial spaceflight, something that just a few years ago was headline news, barely registered a blip. This vacuum of attention became its own story, fueling uncomfortable questions. Did it really happen as described? Was the lack of publicity intentional? Contrast this with a Blue Origin flight just 6 months earlier, in April 2025. That mission exploded into public consciousness, but not in the way the company wanted. It was flooded with conspiracy theories. People claimed the flight was faked, analyzing every frame of footage for green screens, CGI, and anomalous hair behavior in zero gravity. Every detail became evidence of deception. We have 2 flights, one generating a firestorm of doubt, the other met with an eerie silence. Which is more suspicious? The point is not to validate the conspiracies, but to observe the phenomenon. We project narratives onto ambiguous events, and we do the exact same thing with natural mysteries in the cosmos. Think about Oumuamua in 2017. It was elongated, tumbling, and, most critically, accelerating away from the sun faster than gravity alone could explain. Scientists proposed natural explanations, outgassing of invisible gases like hydrogen or radiation pressure on an object of incredibly low density. But a subset of scientists, most notably Harvard's Avi Loeb, proposed something else. What if it was an artificial light sail, a thin sheet of material pushed by starlight, either an active probe or a piece of derelict alien technology? The same happened with Tabby's star, a star showing bizarre, deep, and irregular dips in brightness. The most sensational hypothesis was an alien megastructure, a vast swarm of solar collectors. The leading scientific explanation is now a cloud of circumstellar dust, evidenced by the fact that the star's light is dimmed more in blue wavelengths than in red, something a solid object wouldn't do. Every mystery, Orsees, fast radio bursts, 3i Atlas, becomes a screen onto which we project our deepest hopes and fears. Are we alone? We have an existential longing for contact, and every anomaly is a door that might open onto something extraordinary. 3i Atlas is a mirror. In its glowing green coma, we see reflected our own curiosity, our hunger for meaning, our hope that the universe is stranger than we imagine. And maybe it is. But for now, we have a comet. A weird, fascinating, but probably natural comet. And that's enough, because even natural mysteries are extraordinary. Let's zoom out and piece this all together. 3i Atlas isn't just a single oddity. It's a profound message, a data point in a galactic library that we are only just beginning to read. Imagine the galaxy as an archive. Over billions of years, every planetary system that forms is a chaotic construction site. Planets migrate, gravitational tugs of war ensue, and countless comets and asteroids are ejected, flung out into interstellar space. Each of these objects is a message in a bottle, carrying a pristine sample of the chemistry of its home system. Oumuamua was a bottle, 2i Borisov was another. 3i Atlas is the latest to wash up on our shore. And so far, all three have been wildly different. This implies that the diversity of planetary system chemistries in the galaxy is staggering. Perhaps our solar system, with its water-rich comets, is the oddball. The nickel anomaly is a key part of that message. It's a chemical fingerprint telling us about the star factory, where 3I Atlas was born. If it truly comes from the thick disk, it's a direct sample of the chemical evolution of our galaxy from a bygone era. It's a piece of a star system that might be billions of years old and thousands of light years away. We are reading history, written in atoms, and there are more of these messages out there. Based on the detection rate of these first three visitors, astronomers estimate that at any given moment, there are several interstellar objects within the orbit of Jupiter, small, dark, and moving fast. We are missing thousands. But with the Vera C. Rubin Observatory set to find at least one per month, we are about to go from a few anecdotes to a true statistical sample. In a decade, we could have a catalog of over 100 interstellar visitors. We could start to map the galaxy chemically, correlating comet compositions with their trajectories. Comets from that direction are carbon-rich. Comets from over there are nitrogen-rich. We could use comets as tracers of galactic structure. 3I Atlas is just one entry in a growing stack of anomalies. We live in a new era of astronomy, where our instruments are so powerful, we are finding things faster than we can explain them. We are in a golden age of anomalies. This is both exciting and dangerous. It's exciting because anomalies drive new physics. It's dangerous because the hype can outpace the science, eroding credibility. The key is to maintain both skepticism and wonder. So, what is 3I Atlas? Is it alive? Poetically, yes. It's dynamic and changing, behaving in ways that feel purposeful. Literally, almost certainly not. The most likely explanation is that it is a natural comet, but one formed under conditions so different from our own that it challenges our every assumption. An ancient, carbon dioxide-dominated body from a metal-poor star system. Its surface chemistry altered by eons of interstellar radiation. Its interior layered with exotic ices that are now activating in sequence as it feels the warmth of our sun for the first and only time. It is a reminder that nature, given billions of years and trillions of star systems, has explored a parameter space of chemistry and physics far vaster than we have ever imagined. The next steps are clear. Watch this comet obsessively as it approaches the sun. Measure everything and prepare for the next visitor and the one after that. One day, we will intercept one. We will land on it, drill into it, and bring a piece of another world back to Earth. Until then, we watch, we measure, we wonder. Atlas came from somewhere out there, carrying a message written in water and nickel and cyanide. We didn't ask for it, and we don't fully understand it yet, but we are listening. We are learning. And in that stubborn insistence on understanding, we find something that might be the closest thing to alive in this whole story. Not the comet, us, curious, wondering, reaching out to touch something that came from impossibly far away. The universe keeps sending these letters from the dark, and every time one arrives, we're reminded that we live in a vast, ancient, incomprehensibly rich cosmos. A cosmos that will forever surprise us, forever offer new mysteries to solve. 3 Atlas is one such mystery, and whether its secrets yield easily or resist for decades, we'll keep looking. We'll keep asking. We'll keep listening for what the universe is trying to tell us, because that's what it means to be human. To see something strange in the night sky and to refuse to look away.